all right? I told the guys to scan it in, but I didn't have a place for them to scan it. So they scanned it, but it hasn't been uploaded yet, so they don't have a chance to, they will not have a chance to grade it. But I have a makeup Monday anyway, so you're not going to get your grades before Monday afternoon or Monday evening. So yesterday we were talking about equilibrium constants. In chapter 14, we talked about rate constants and how rate constants tell us how fast a reaction goes. The equilibrium constant is the ratio of the rate constants for a reversible reaction in which we can get a forward reaction and a reverse reaction happening at the same time. So the reaction looks like it's stopped, and we can now calculate concentrations. That worked very well in the rate law when we had the slow step being the second step, because we could allow the first one to go to equilibrium. The concentrations look like they're steady now, and it allowed us to put in a concentration for an intermediate. So we showed how to do equilibrium constants. Now the question is, who cares? I will tell you that for most of you, a lot of what we're doing this semester will not be applicable in the rest of your life. But this is what we do in 1128. We do kinetics, we do mechanisms, we do equilibrium. And I'll be perfectly honest with you, I don't know why that's the way it's been set up. Because the majority of people that take Gen Chem are either pre-meds, who really don't need this, or pre-engineers who have their own class in this stuff. So I really don't understand. I know when you take 2 semesters of biology, it's 1107 cell biology and 1108 botany. I'm absolutely convinced it's because people with degrees in botany can't find other jobs, so they have to give them something to do. But any chemist could teach this, so I don't understand exactly why we do this, but this is the ACS schedule. I don't have anything to do with it. ACS sets it up, and this is what they tell us we have to do. So I'm sorry that none of this has a lot of real applicability to your real life. So the equilibrium constant tells us, and I've got KEQ here. KEQ can be used for anything. We saw KC on Tuesday for concentrations. We saw a KP for pressures. We will see a KA, a KB, a KW, a KSP. So just in general, we can say KEQ, that will apply to any equilibrium constant with any other subscript. So we know that the equilibrium constant tells us how well the reaction proceeds. How many products are we going to get out of this reaction? But what else do we use K sub C for? One thing we could do is use it to determine whether or not a reaction is at equilibrium. At equilibrium, we have a K value. How do we know if we're not at equilibrium? Well, if we're not at equilibrium, K is a constant and it's set. We know what K should be for every reaction. And we can solve for something that looks like K, but if it doesn't equal K, we know that we're not at equilibrium. And if we're not at equilibrium, it will tell us, do we have too many reactants and the reaction will go forward, or do we have too many products and the reaction will go backwards? Remember, this only works for reversible reactions. So we have something called Q, the reaction quotient. The equation for Q is exactly the same as the equation for K. It is products over reactants. It's exactly the same as K. The reaction quotient is used to determine whether or not we're at equilibrium to indicate the amount of products and reactions we have at any given time, whether we're at equilibrium or not. So this formula for Q, that's equivalent to K sub C, Q sub C, is exactly the same as K sub C. It's exactly the same. It's always products over reactants. So if we're given a problem, if you're given a problem, that asks if this reaction is at equilibrium, and if it's not, which direction will it go, the first thing you do is set up to find Q. You put in the information that they give you, and then you can compare Q to K. If I have all reactants and no products, products over reactants will be 0 over something. So Q sub C is equal to 0. But if I have all reactants and no products, I know the reaction is going to go forward. I don't have any other option. It's going to go forward. I wasn't worried about that before, but the guy who has the office next to mine across the hall came back from vacation this week. So, again, all reactants, no products. Obviously, the reaction is going to go forward. If I have all products and no reactants, then I've got a number over 0, and my Q is infinity. But again, if I have all products and no reactants, the reaction has to go backwards. There's no other option. The question is, when I have both products and reactants, where do I stand in terms of the reaction? So at any other time in the reaction, except when we have all reactants or all products, we want to compare Q to Kc. If Q is greater than K, that means the numerator is too large, there are too many products and not enough reactants. If I have too many products and not enough reactants, I need to straighten that out by removing some of the products. So when Q is greater than K, the reaction, whoops, I knew this was a problem. I just pulled this slide from last semester, and I knew this was a problem last semester, so let me fix it. So, when Q sub C is greater than K, I have too many products, not enough reactants, so the reaction is going to go in reverse. And the reaction will continue to go in reverse until we reach an equilibrium state. It doesn't go in reverse forever. It just goes in reverse until we reach an equilibrium state. If Q is less than K, then I have too few products and too many reactants. I need more in the numerator. So now, if I have Q less than K, I need to make more products, and therefore the reaction is going to go forward. Hang on one second. I wasn't sure this person was here because she's got her head buried. Email him. He's willing to tutor you. Sorry about that, guys. I wanted to make sure she got it before she left class. So, okay, so by comparing Q to K, we know, are we at equilibrium or not? If Q equals K, we're at equilibrium. We don't need to do anything. But if Q is greater than K, we have too many products, too many things in the numerator, we have to go backwards. If Q is less than K, I have too few things in the numerator, I need to go forward. So the value of Q compared to K tells us, are we at equilibrium? And if we're not, which direction will the reaction go? So this is just pictorial of exactly what I've been saying. When Q is less than K, it moves forward till it reaches an equilibrium where Q is equal to K. When Q is greater than K, it goes backwards until you get an equilibrium where, again, Q is equal to K. And written out, exactly what I've been saying. I say all this stuff, but if you're like me, audio is nothing for me. I don't grasp anything that's audio, to the point where I watch my television with the closed captioning on all the time because I need to see it. Some people are more visual, some people like words, so I say things for the audio. I show a picture for people that like pictures, and then everything I've said is in a word here. Okay? So I'm just repeating things over and over in various forms for people that have various learning styles. So here's a practice problem. I have the Haber process again. We really like the Haber process in chemistry. We like the Haber process because it's a nice, simple reaction, but it's not all one-to-one. And that's part of what we like about it. It has coefficients in it. Okay. So I have, obviously it's giving me an atmosphere, so I'm going to be looking at a K sub P versus Q sub P. My K sub P is 41. It's not a great value. When we get through with this reaction, we have a pretty good mixture of all the things. At the time they measure it, there is 0.124 atmospheres of nitrogen, 0.113 atmospheres of hydrogen, and 0.00682 atmospheres of ammonia. Now, looking at that, you might say, well, obviously it's going to go forward because I don't have a lot of ammonia. But I really don't know that for a fact because I've got N2 and H2 in the denominator, and H2 is cubed. So I can't just look at it and say, well, I don't have a lot of NH3, so it's got to go forward. I've got to actually check. So my Q is the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. So I just plug in those numbers. 0.00682 squared divided by 0.124 times 0.113 cubed. And my Q comes out to be 0.260. 260 is way smaller than 41. So my guess that it was going to go forward is true, but I couldn't do it unless that I actually got a number for it. So with Q that much lower than K, the reaction is definitely going to go forward. Okay, so now I have a generic reaction that X plus Y goes to Z. K is equal to exactly 1. If everything is 2 molar, my denominator is going to have 2 times 2. The numerator is going to have 2. So I'm going to end up with a number that is not equal to 1. I'm not at equilibrium. My K and Q are not going to be equal. My Q value is Z divided by X times Y. It's 2 divided by 2 times 2. It's 0.5. and Q is less than K, so the reaction goes forward. I could see, because they gave me a really nice K of only 1, that it was not going to come out to be 1 if I had 2 divided by 2 times 2. I saw that without having to do the numbers, but I didn't know exactly what the number was going to be, so I went ahead and calculated the value. But what happens if I do part B? Now, when I do part B, I still have 2 things in the denominator and only 1 thing in the numerator, but they're all 1. So I'm working with atmospheres now. If I'm working with atmospheres, I should be converting to K sub P. If I convert to K sub P, then my K sub C equals K sub P times RT to the delta N. Delta N here is equal to -1. So my K sub P should be equal to 1 divided by 0.08206 times 300, and my K sub P is equal to 0.0406. So now when I plug things into my sorry, I was looking to be able to see if I could move this out of the way. There we go. When I plug in my Q, it's 1 over 1 times 1, so it's just 1. But now my Q is greater than my Kp. If my Q is greater than my Kp, then the reaction needs to go in reverse. So they gave me the first one in molarity, and they gave me a K sub C. The second one they gave me in atmospheres, so I needed to convert to K sub P, which, if you're looking at the original slideshow, I didn't do. So I will fix that and repost it. Oh, okay, never mind. I did redo it. I didn't realize it. So if I do it this way, sorry guys. The other day I was telling you I was having a really bad day. So I tried to plan ahead on all of this, and I did plan ahead on all of this. I just didn't realize the next slide was going to make the correction I needed to do. So in this case, Q is equal to K the way I solved it. So this is equilibrium. Usually I have a few minutes before class to review the slides, but I have a meeting immediately after this class, and I was trying to print out all my notes for that. So, sorry. But the next slide does tell me that I did this wrong, because these were all atmospheres, and I compared it to a K sub C. So I did my K sub C to K sub P, and good thing I had this because I apparently did it backwards on the previous page. K sub P is equal to K sub C, RT to the delta N. Delta N is 1 minus 2, and so my value for K sub P is 12.2. Now, my Q was 1. If my Q is 1, then Q is less than K, and the reaction needs to go forward. Now, again, I could have made a hypothesis here. My hypothesis is that when all of the atmosphere values are exactly the same, that gives me 2 atmospheres of pressure on the reactant side and 1 pressure on the product side. And reactions like to go so they can equalize pressure, even out the pressure. So I could make the hypothesis that it is going to go forward, but again, I can't just guess, I have to do the numbers. Okay. Sorry guys, I'm just putting in some animation so it doesn't all show up at once. Now in this one, they actually give me a K sub P. All my things are in the gaseous state. That is the only time I can use a K sub P, is when everything is in the gaseous state. So it gives me a K sub P, and it gives me a series of partial pressures. This container now has 3.5 atmospheres of CO, 0.71 atmospheres of H2O, 2.6 atmospheres of CO2, and 0.86 atmospheres of H2. Now, looking at those numbers, I can't make a guess. I mean, I suppose I could make a guess that says 3.5 plus 0.71 is 4.2, 2.6 plus 0.86 is 3.5, and maybe it's going to go forward because the pressure is actually lower on the product side. But with all these numbers, it's hard for me to tell what's going to go on. So I have to find Q. So my Q is products over reactants. It's 2.6 for CO2 times 0.86 for hydrogen divided by 3.5 for CO and 0.71 for the H2O. So my Q value is 0.90. So Q is less than K, and my guess was correct. The reaction is going to go forward. But again, I can't know that for sure unless I actually do the numbers. So this is one of the things that we can use K and Q for, is the reaction at equilibrium. Not super useful because we're probably not going to keep wanting to take samples of it to say, is it at equilibrium yet? We probably just let it go. But this does allow us to say, this is not at equilibrium yet. We're going to make more products or we're going to make more reactants. What we usually do with K is figure out what the equilibrium concentrations look like. How does the concentration change from the start of the reaction to equilibrium? We saw that when we were looking at the integrated rate laws, over time, we saw that the concentration would go down. Eventually, the concentration, when we reach equilibrium, stabilizes, and we get the same concentration. But what is that going to be? For something like the Haber process, this becomes important. How much nitrogen and how much hydrogen do I have to put into the system to get a certain amount of ammonia out for industrial uses? This is something that they do use a lot in industry to say, when I get to equilibrium, how much of this product am I going to have? It basically tells us whether we've got a good reaction or not. Are we going to get a good amount of product? Because that's what we want. So, finding equilibrium. If I'm given the initial concentrations and I'm given one final concentration, I should be able to find the rest of the final concentrations. Now, in 1127, the most hated thing students complained about was usually stoichiometry, having to balance an equation. We're now going to introduce you to the most hated part of 1128. In order to find these values, we have to create a table. And we're going to create something known as an icebox. So I have, again, PCl5 decomposing to PCl3 in chlorine gas. It's giving me moles of material. Now, moles of material can't be used. I have to convert them to molarities to use in a K value, but it's all in a 1 liter flask. So the values of the moles will be the values of the molarity, because it'll just be moles divided by 1 liter. It's telling me that I'm starting with no chlorine whatsoever. I'm starting with PCl3 and PCl5. At equilibrium, I've created some Cl2. If I start with no Cl2, I have to have the reaction go forward. I've created a certain amount of Cl2. How much PCl5 and PCl3 do I have left? So, important thing, make sure all of your concentrations are in molarities. In this case, it was the same as the moles. I just divided by 1. And this is what an icebox looks like. ICE stands for initial, change, and equilibrium. Your 3 rows will be the initial concentrations of your reactants and products. The change is how much you make or lose. And equilibrium is exactly what it says, the equilibrium concentration of these things. The number of columns you have is 1 plus the number of reactants and products you have, because the first column has to say ICE. So what do I know? Well, I know that my initial concentration of PCl5 was 8.7 times 10 to the minus 3 and 0.298 for PCl3, and I had no chlorine. But I do know what the equilibrium concentration is for chlorine. It's 2.0 times 10 to the minus 3. So 2.0 plus 2.0 times 10 to the minus 3 is the change that I have for the chlorine. So once I put in all of the material, all of the data that they give me in the problem, then I look to see what else can I fill in the box. And I can fill in what the change for chlorine must be, because I went from 0 to 2.0 times 10 to the minus 3. But the reaction is PCl5 goes to PCl3 plus PCl2. It's all a 1-to-1 relationship, which means if I make that much chlorine, I have to make that much PCl3 as well. Remember, my reaction is PCl5 goes to PCl3 plus Cl2. So whatever my change is for the Cl2, it has to be exactly the same for the PCl3, because for every chlorine I make, I also make a PCl3. So that has to be exactly the same, because it's a 1-to-1 relationship. Every time I make a chlorine, I make a PCl3. But every time I make a chlorine or a PCl3, I lose that amount of PCl5. So my change for PCl5 is negative 2.0 times 10 to the minus 3. Okay. When you're doing the icebox, stoichiometry matters. Since this is all 1-to-1, I know that if I make this much chlorine, I have to make that much PCl3, and I have to lose that amount of PCl5. So 0.298 plus 2.0 times 10 to the minus 3 is 0.300 molar. 8.70 times 10 to the minus 3 minus 2.0 times 10 to the minus 3 is 6.7 times 10 to the minus 3 molar. These are now my equilibrium concentrations. From this equilibrium concentration, I could then find what is the K value for this reaction. So the K value for this reaction, is just 0.3 times 2.0 times 10 to the minus 3 divided by 6.7 times 10 to the minus 3. So once I get all the equilibrium concentrations, I can find my K value. So in this case, my K is equal to 8.96 times 10 to the minus 2. This is not a great reaction under normal conditions. The condition that it gives me here is it doesn't say, it just says at a certain temperature. At room temperature, this is not a great reaction. It doesn't produce a lot of product. And we can see that because we've got a fairly low K value. So this is one of the things, first thing we can do with K is to take all of the numbers that they give us, put them into an equation that looks like K, and figure out if we're at equilibrium, and if we're not, which way are we going to go. The second thing that we could do is to take a certain amount of initial concentrations of reactants, products, it doesn't make any difference which one, and then figure out what is going to happen to them at equilibrium, and then find a K value. So that's the second thing I can do, is to do an experiment to find K by putting in a certain amount of material and then going ahead and finding my K value. So here's another one. H2 plus I2 goes to 2HI. My initial concentrations are 0.5 molar H2 and 0.5 molar, 5 mole I2, but they're in 1 liter, so I can use these as molarities. So 0.500 molar, 0.500 molar I2. At the final concentration, I have 0.900 moles or 0.900 molar HI. Now this one's going to be a little different because I've got stoichiometry here. It's not one-to-one with everything. So I make my icebox and I put in everything that I know. So I had 0.5 molar H2, 0.5 molar I2, no HI to start, but 0.9 molar HI when I'm done. Now the change for HI is obvious. The change for HI is +9. What becomes not so obvious is the fact that there is now a stoichiometry. So the amount of H2 that I lose to create HI, the amount of I2 that I lose to make HI is not 0.9, because one H2 and one I2 make 2 HIs. So I have to take the stoichiometry into account. So I divide by the stoichiometric coefficient. So the change in I2 is, is -9 because it is a reactant, divided by 2, which is the stoichiometric coefficient of the HI. So I have to take the stoichiometric coefficient of HI, which is 2, and divide that into I2 because the amount of I2 that disappears is half the amount of HI I make. And then H2 will be exactly the same, minus 0.9 divided by 2. So if you have a stoichiometric coefficient for something, and you're looking at everything else, we have to take that stoichiometric coefficient into account and divide other things by it. Because one H2 makes two HIs, so 0.450 H2 makes 0.9 HI. Make sense? Yeah? So I had to divide by 2 because HI had a 2 in front of it. So now my equilibrium is 0.050. This is negative 0.450. This is negative 0.450. So my equilibrium concentrations of H2 and I2 are 0.050 molar. So now again, I had equilibrium concentrations. I can find K. So K is HI squared. Again, we have to make sure we use that coefficient. Divided by H2 times I2. It's 0.9 squared divided by 0.05 times 0.05. My K is 324. This is a pretty decent reaction. You put hydrogen in with iodine, and it makes HI fairly readily. So the difference between this one and the previous one is I had stoichiometric coefficients. And we have to assume that just like with the rate constants that we had, where if you have a stoichiometric coefficient, it changes how it compares to something else. So we have to take the number we're given, in this case our HI, and divide it by its stoichiometric coefficient to find the other things. It's exactly the same as we did with 1 over A equals A over delta T, 1 over B equals B over delta T. We have to take that into account. So now I've got CO, H2O, H2, and CO2. This is actually a process they use to remove carbon monoxide if they have a situation where there's like a buildup of carbon monoxide. You can spray steam into it, and it will give you CO2, but it also produces H2, which is kind of flammable. So you either get toxic, you got flammable. So now I have 0.00925 moles of carbon monoxide and 0.202 moles of water, steam. And now they're not in a 1 molar flask. Now they're in a 0.5, not molar, liter flask. So now I do have to convert to molarities. So I have to take the moles, divide them by the liters, and get the new molarities. So I took 0.00925, divided it by 0.5, 0.02 divided it by 0.5, and my final amount of CO2, 0.00825 divided by 0.5. These are my molarities. The numbers they give me are not. So again, I'm going to put them into the icebox. Okay, I can't do animations on this one because I just typed everything into the table. So I started with 0 amount of CO2, and at the end I had 0.0165. So my change for that is 0.0165. But this is all 1-to-1 again. So the amount of H2 I create is the same as the amount of CO2 I create. The amount of CO2 I create is the amount of H2O or CO that is removed. So minus 0.0165 for the reactants plus 0.0165 for the products. So my final equilibrium is 0.00215 for CO, 0.0235 for H2O, and 0.0165 for both H2 and CO2. Now in this case, you notice I had just reactants to start with. So CO2, which is what they give me for my final, is 0 to start, but so is H2. I didn't have any H2 in here to start. So my K is H2 over CO2, H2 times CO2 divided by CO times H2O, 0.0165 times 0.0165 divided by all of that stuff, and my K is 53.9. So it doesn't make any difference what I start with. I can start with just one. I could have started with just how much CO do I have. As long as I have one final concentration, I can fill in everything else. So I need at least one initial concentration and one final concentration to figure out what K is here. Okay, SO3 decomposes to SO2. I'm going through this a lot because ice boxes are like the main thing you're going to see on the next test. The next test will be chapters 15 and 16. Ice boxes is all what chapter 15 is all about. Chapter 16 then applies the ice boxes to acids and bases, but they're actually a little easier with acids and bases. So I have 0.15 moles of SO3, but again, it's in a 1 liter vessel, so that becomes my molarity, and it tells me how much SO3 I have left. So I was saying, all I need is one initial concentration, one final concentration, and that's all they're giving me. The initial concentration of SO3 and the final concentration of SO3. But I can fill in everything else as long as I have one initial and one final. And they can be for the same thing. So initially I have 0.150 SO3 and no SO2 or O2. I do have to take into account the 2's. My equilibrium is 0.0076. So my change for that is 0.150 minus 0.0076. So it's negative 0.1424. But that's equivalent to a 2x because there's two SO3s. But then when I look at SO2, SO2 also has a 2 in front of it. So its increase will be equal to 2x. So its increase is the same as the decrease in SO3. It's 0.1424. But oxygen is half of that because there's only one oxygen. So if oxygen is only X, I divided 0.1424 by 2. So this 0.712 that I got was 0.1424 divided by 2. So I had to divide that value by the stoichiometric coefficient of the thing I'm given to start with. So those are my equilibrium values for everything, given just how much SO3 do I have to start and how much SO3 do I have at the end. Like I said, one initial, one final, it's all I need. If I don't have any other initial concentrations, everything else must be 0. So my K value is SO2 squared times O2 divided by SO3 squared. So 0.1424 squared times 0.0712 divided by 0.0076 squared. And my K value is 25. Okay, in this case, they want me to find K for something where it gives me the initial concentration of one of the reactants and one of the products, and then the equilibrium concentration for that product. Now, look closely at this reaction. It gives me AB, and it gives me A2D. It doesn't have to tell me anything about C2D and CB because they are both solids. And solids are not included in our equilibrium constants. Solids and liquids are not included, only things that say G or AQ are. So when I set up my ice box, those are the only two things I need. Okay, so I start with 0.3 of each of them, and at the end, I have 0.20 A2D. Now, my A2D went down. If my A2D went down, then what's happening to my AB? Okay, I had everything going down and I shouldn't, because if A2D is going down, that means the reaction is going backwards. It's going in reverse. So if A2D is going down, then AB must be going up by the same amount. Nope, but not by the same amount, by twice as much. Because A2D goes down by 0.1, but AB is twice that. So 0.1 is X. My concentration change for AB is 2X. So looking at this, I don't know what K is, I don't know what Q is, so I don't know whether it's going to go forward or backwards, but I have to make the assumption that if A2D is going down, the reaction must be going backwards, which means AB would have to go up. And it goes up by twice as much as what A2D goes down by. So now, when I put in the K, it's just A2D divided by AB squared. So it's 0.2 divided by 0.5 squared. So my K value is 0.80. Okay, so this one was put in just to note that everything else we did, the reaction was going forward. Reaction doesn't have to go forward. Reaction can go in reverse. And we know whether it's going in reverse by how the concentrations change. If the concentration of a reactant goes up or the concentration of a product goes down, I know the reaction's going in reverse. But I set up everything exactly the same way. It's just where do I put my positives and where do I put my negatives? Okay, it's 10 of 10. We finished one type of icebox. Let's take a break before we start doing the other type of icebox. Okay, the reason I took a break is because what we just did with iceboxes is actually the easy one. Because we can fill in every single one of the boxes. We know what is available, what we can change. We're going to start with this section where we don't know where things are. We don't know what's going on. We have a K and we have an initial concentration and we have no idea what is going to happen. So I figured we'd take a break, let your brain settle a little bit before we got into this one, which is worse. Okay, this one's not too bad. I have a concentration of carbon monoxide and a concentration of water. And earlier, the K value was calculated as 5.8. Sorry. So we have a K, we have some initial concentrations. Now, when we're doing this one, well, when we're doing any of them really, we have to make sure the equation is balanced. So we don't ask you to balance an equation, we just ask you to make sure it's going to be balanced. On a test, it will always be balanced. I can't guarantee it's always balanced on the homework. The homework, which I haven't written yet, that's supposed to be due Saturday. I'll postpone a little bit. I was so busy trying to get an exam written and a key for the exam and all of that sort of stuff, I completely forgot about homework. Homework for this weekend will be the end of chapter 14, mechanisms, and chapter 15, the stuff we did on Tuesday, where we just introduced k-values. The homework that will be due next Wednesday will include doing this. It will be predominantly iceboxes. So just make sure when it gives you a problem that your equation is balanced. So this equation is balanced as is, because I'm just moving an oxygen from the water to the CO2. And K is CO2 times H2 divided by H2O and CO. And I know that K is 5.8. Gave me that in the problem. So here's my icebox. 0.0125 molar H2O, 0.0125 molar CO. No CO2, no H2O. I don't have a final concentration here. I don't have any change here. How do I fill this in? Well, the first thing I need to do is figure out which direction this is going. Is it going forward or backwards? Now, Q is obviously 0 because I have no products. So Q is going to be less than K no matter what the size of K is. The reaction has to go forward. Okay. No products, don't have a choice. It's got to go forward. Anytime you have zeros, hopefully the zeros are on only one side. It's going to go to that side. So I know it's going to go forward. So whatever is on my product side, the CO2 and the H2, has to be positive. Whatever on the reactant side has to be negative. But positive what, negative what? No idea. X. I don't know what these change values are. So I'm going to put X, I'm going to put X, and on this side, it will be minus X. Hold on a second. I'm in the wrong file. This is the one I want. Sorry, I pulled up the blank one because I was making changes on it, but I want the one that's already got writing on it. So I'm going to put in plus X, minus X, minus X. I have no idea what the change is, so I have to set it as a variable. But now, my equilibrium concentrations have X's in them. X, 0.0125 minus X, 0.0125 minus X. These are the values I then have to put into my K equation. So K is X times X divided by 0.0125 minus X times 0.0125 minus X, and that equals 5.8. Now, I could FOIL the bottom, move it to the left-hand side, multiply it all by 5.8, then put it into a quadratic equation and solve. I do not want to do a quadratic equation. You guys don't want to do a quadratic equation. So if I look at this, I see something that will make this easier to solve. This is a problem that contains squares. It's 5.8 equals X squared over 0.0125 minus X squared. If that's the case, if everything I have on the right-hand side is squared, when I solve for x, I have a problem that's referred to as a perfect square. I can take the square root of both sides and not mess anything up. A perfect square problem says that both sides are the square of something. And therefore, I can take the square root of both of them. So I'm going to take the square root of 5.8 and just make it equal to x over 0.0125 minus x. Now I don't have a quadratic. I do have to do some algebra, but I don't have a quadratic. There's no x squared anymore. So the square root of 5.8 is 2.4. And then I'm going to bring the 0.0125 minus x over to the left-hand side and multiply the whole thing by 2.4. Just told you guys, this is an algebra class. Got to learn how to do your algebra. So 2.4 times 0.0125 minus x equals x. I multiplied the 2.4 through. Then I moved the 2.4x to the other side. I have 0.0301 equals 3.4x. X is equal to 0.034 divided by 3.4, or 0.0885. I now have an x. Took a little manipulating, had to put in the equation, take the square root of both sides, move the denominator over to the other side, multiply through, separate like terms. It took a little bit of a manipulation, algebra manipulation, but I have an x. Now that I have an x, I can put the x back in the icebox. You can see why I said we were taking a break before we started this, because your brain needed a break. So now I just put those x's into my icebox. So minus 0.0885 for both CO and H2O, plus 0.0885 for CO2 and H2. So my values become 0.0365 times 0.0365 and 0.0885 and 0.0885. Now, I do have a way to double check that my answers are correct. And that is to put them back into the equation for K and see if it comes out to be 5.8. So a double check for the answer being correct is, does this equal K? So 0.0885 times 0.0885 divided by 0.0365 times 0.0365. Okay, it's a little off. We originally said it was 5.8, and my calculator gives me 5.9, but precision is plus or minus 1 in the last decimal place, so 5.8 and 5.9 to this decimal place are the same value. So it worked. The reason it's not 5.8 is simply a rounding thing. Rounding differences make no difference on a test as long as you're within plus or minus a certain amount. And in this case, it's plus or minus 1 in the last decimal place. So this is just a way to check that my final answers are correct. Put them back into the K equation and see if you get the actual K value back. Okay, suppose I start with a mixture of reactants and products. Well, if I start with a mixture of reactants and products, then the first thing I have to do is Q and figure out whether it's going forward or backwards, so I know where to put the plus x's and the minus x's. So I have 3 moles of everything in a 1.5 liter flask. So I did have to convert to molarity. So 3 moles divided by 1.5, everything is 2 molar. My equilibrium constant is 115. 1.15 times 10 to the second, it's 115. So first thing I want to do is find Q. So 2.0 squared divided by 2.0 times 2.0
Q is 1. 1 is less than 115. So the reaction is going to go forward. That means I'm going to put my plus x's on the product side and my minus x's on the reactant side. So I put plus x, except that the balanced equation is H2 plus F2 goes to 2HF. Have to use that stoichiometric coefficient. So I set the disappearance of H2 and the disappearance of I2 as x, and the appearance of HF as 2x. Otherwise, I'd have to be doing x and half x's, and I don't want to do that. So I just set x's with the stoichiometric coefficient in front of them, and so I get minus x plus 2x. So now I have 2.0 minus x, 2.0 minus x, and 2.0 plus 2x. Now, we like perfect squares because we like the fact that we can just take the square root of everything, don't have to attempt to do a quadratic. You will not get a quadratic on a test. I told students that spring of 2025 that they would not get a quadratic on the test, but I didn't write the test, Dr. Katie did, and there was a quadratic on it. You do not have time, even with your graphing calculators, you don't have time to sit and try and do a quadratic in a test, particularly in his tests, which are only 50 minutes long. So you will not see a quadratic on the test. I have two cheats. The first one is this perfect square. There will be another cheat that we can talk about, which will be very useful when we get into chapter 16. And you can always apply one of those cheats to a problem I give you. So now I have Kc equals hf squared divided by f2 times h2. Now the fact that I have hf squared in the numerator and h2 and f2 were the same means I still have a perfect square. If f2 and h2 were not the same, I would not have a perfect square, but I have a perfect square. 2 plus 2x is squared, and 2 minus x squared. So when I solve for x, I'm going to use the perfect square cheat. I'm going to take the square root of both sides. So the square root of 115 is equal to 2 plus 2x divided by 2 minus x. Square root of 115 is 10.7. I don't need that there. So first thing I'm going to do is multiply both sides by 2 minus x. Then I'm going to carry the 10.7 distributed across the 2 minus x. So I have 21.4 minus 10.7x equals 2 plus 2x. I'm going to move all the numbers to the left side, all the x values to the right. So I have 21.4 minus 2x minus 2 equals 10.7x plus 2x. Now, the reason I'm moving in this case all the numbers to the left and all the x values to the right is because that gives me positive values on both sides. I could have moved it the other way around and moved 2x to the left, but then I'd have minus 12.7x. I just don't like negative numbers if I can avoid them. So 19.4 equals 12.7x. X is equal to 1.53. So more algebra, but no quadratic equations. So I put everything back in. My x value is 1.53. So H2 is 2 minus 1.53. F2 is 2 minus 1.53. So both of those are 0.47. My HF is 2 plus 2x. So 2 plus 2 times 1.53, which gives me 5.06. And then I did a check, where I just put it back into the K. And again, I'm off by a value of 1 in the last decimal place. That's perfectly fine, that's precision. So doing that is just a way to check that your numbers are correct. Because if I get something like 3,842, I know my numbers aren't right. I need to get something close to 115. So this one was a little bit different simply because we needed to know which direction it went. We had to use the Q to figure out what direction it went, and then we had to take the stoichiometric coefficient into account. So it was a little more difficult than the first one we did. But the fact that we took the stoichiometric coefficient into account gave me a square on the top and still gave me a perfect square to solve. Okay, so problem-solving strategy. Make sure your equation is balanced. Write the equilibrium expression using the law of mass action. Your book talks all about the law of mass action. All the law of mass action says is the direction of the equilibrium and what the final equilibrium constant is just depends on how the reaction's going. So we can ignore that. Just write your equilibrium expression and list your initial concentrations. In this case, put them in your icebox. Then, if any of them are not zero, or any of them are zero, I should say. If any of them are zero, you can skip step 4, but if all of them are non-zero, you must find Q and figure out the direction of the equilibrium. And then put plus x's and minus x's multiplied by the stoichiometric coefficients appropriately depending on which direction the reaction is going. Substitute all of that into your icebox, solve for x. Then once you solve for x, you can do this. Number 6 is putting everything into your change box. Then you're going to put everything into your equilibrium box, and you're going to solve for what the final concentrations are, and then you're going to plug them back into K just to make sure your answer is correct. Okay, so that one was a little more difficult. We don't want to go too crazy with your brains today. So 3 things. 1, what is Q and how do we find a Q? 2, what does Q tell us? Compare Q to K to see which direction something's going. Then use an icebox where you're given something and a final concentration, either a K or an initial concentration and a final concentration. The ones that give you final concentrations are a little easier to do because you can already know what your changes are. For the ones that give you K and just an initial concentration, you have to put in your X's. Now, we're going to stop here because I've filled your brain with a lot of stuff. Tomorrow we're going to do more Ks, but I'm going to show you the second cheat that we can do so we don't ever have to do a quadratic. Okay? You guys have a good afternoon. The weather is supposed to be absolutely beautiful. It's only supposed to go up to 80 degrees, not 95, and the sun is out, so enjoy the afternoon.